Hi everyone, this is another web video. This one is dealing with the concept of fraction dissociation. This is directly related to a lot of the acid-base stuff we're going to be talking about. It's something you'll find pretty common, and it's a handy way to think about what percent of your acid or base is in the either protonated or deprotonated form in a solution. So this is from around page 168 in your textbook. Alright, so this fraction dissociation is a handy way of thinking about the amount of your acid or base that is in each form. It's a handy way that people describe it. And so when we're talking about a weak acid, weak base situation, we talk about it in a real generic sense. We're talking about HA, which we know is in equilibrium with its conjugate base, which we'll call A minus. And we know that this is governed by a Ka. Or it's at least described by Ka. And so we'll say this Ka equals the concentration of the products over the concentration of the reactants. And as you may recall, in a situation when we discussed this briefly in class, this is written about in detail in your textbook around page 168, that if we're making a solution, if we put some of this HA into solution, right, you start with your acid, it's going to dissociate. And if we want to find out what the pH was, we would recognize that every time you produce a proton, you're also going to produce the conjugate base. And so we just call this X. And then we said the formal concentration that we started with of HA, every time you produce one of these conjugate bases, you're going to subtract one from your HA. So we would call that as F minus X. All right, and again, this is at formal concentration. So that's the initial concentration. So in terms of alpha, how we describe this is we can use this equation here. So alpha is equal to X over F. All right. So what that means, if you think about that, right, this is your formal, this is the same thing here, right? So this is a concentration of your A minus, right, your dissociated form of your acid over your formal concentration. Okay, so this tells you basically what fraction of your acid has dissociated. Okay, and so if we think about that in terms of what we saw, remember our acid dissociation plot. So let's say we're looking at something like we had pH on the x-axis here, and we wanted to look at something like our A minus. Okay, and again, this is HA goes to H plus A minus. All right, so this should look really familiar. Hopefully you guys recall this from your Pogel exercise. But as we increase pH, so we're increasing our basicity, we're going to increase the amount of our weak acid that is in the conjugate base form. Okay, if you remember somewhere around this inflection point here, this corresponded with the pKa of the acid. Okay, so you can think of this a different way, right? And so in the class we showed that this was, we start with a molarity here. But instead, you can think about this, if you were to divide this by the formal concentration that you started with in your HA, this would actually just be the same thing as alpha. Okay, so in this case I'm going to instead call this alpha, right? And by definition, we are going to have a scale from 0 to 1. So that's telling you is that, high pHs or low pHs at high acidity, this fraction dissociated is very small, but as you increase the pH, you're going to force the reaction this way by consuming your H+, and you're going to increase alpha, or you're increasing this X form. And so that's what we see here, okay? So this is a way to think about this sort of visually. And so it's sort of useful to know, not just in terms of your overall concentration, but lots of times what you really want to know is what percentage of my acid or base is in one form or the other. And this is what alpha tells you. And we can think at this moment here, at this pKa here, right, where the pH equals a pKa, if you remember that, under that situation, we saw this in class, the amount in your protonated and your non-protonated form are the same at this point. In this case, your alpha would be 0.5. That makes sense. So that's what it's telling you, is that 50% of your total acid is in the conjugate base form. So it's half here and half here, which is what gives you essentially, right? So if you had 2 molecules, you would have 1 here and 1 here, and so your formality would be 2, and so your alpha would just be 1 over 2, or 1/2, if that makes sense. Okay, so we're just going to go through a real quick problem here. And this is directly from your textbook, so very close to something from your textbook. So this is, look at page 168. All right, so what we're talking about is a solution of trimethyl ammonium, and so chloride. So this is H and CH3, and this is in equilibrium with H plus and CH3. Okay. So this is what we made. We made a solution of this, right? Even though there's a chloride around, or that's just a spectator ion, what that's telling you is that there's a positive charge on your weak acid here. And so if we want to figure out the fraction associated with this, what we use our Ka, and you see this is on your textbook. Ka equals 1.59 times 10 to the minus 5. All right, and then knowing that, we can use our equilibrium expression. So Ka equals, I'm just going to draw this. So you're going to have your concentration of your conjugate base times the concentration of your acid over the conjugated, over the concentration of the protonated form. And the reason we're setting this up is because, if you recall, we're trying to find what is alpha. Sorry, this is supposed to be a symbol. There we go. That's more like it. What is alpha of a 0.05 molar solution? So if you remember, alpha equals x over f, right? And setting this equation up this way, we can solve and say that this is x, this is x, and this is f minus x, right? And so we can rearrange this into a quadratic, and I'm not actually going to do that. All right, so again, turn to page 168. They actually solve this for you, and you find that x, using the quadratic equation, equals 2.8 times 10 to the minus 6. All right, so now if we want to find alpha, all we do is we use this formula right here. And so alpha equals 2.8 times 10 to the minus 6 molar divided by our initial concentration. Our formal concentration is this here. So it's divided by 0.05 molar. And this gives us our final value for alpha, which is 5.6 times 10 to the minus 5. So remember, this is a fraction, so this is unitless. Another way you can think about this is in terms of percentage, right? If you want to think about this in terms of percentage, this would just tell you that this is your conjugate, your weak acid system here is 0.0056% dissociated. So that means of your trimethylammonium, that 99.995% of it is in this form, and 0.0005% is in this form. So yeah, that would tell you that the vast majority of it is in the protonated form. So this is probably a stronger base than it is an acid. So hopefully that makes sense, and we'll talk about this a bit more in class, and you're going to see this a lot more as we get into more complicated acid systems like polyprotics. The alpha becomes a little more complicated, but it breaks down to the same idea right here. All right, see you in class on Monday.